All right, we only have 2 more days of stuff. 6.1 and 6.2 are the law of sines and law of cosines. So far, our definitions of trigonometric functions have applied to triangles and to angles on the unit circle. But when we applied them to triangles, we were really always talking about right triangles. Yes? Because hypotenuse was part of the definition. Hypotenuse only applies to right triangles. So can you use trig to deal with triangles that aren't right triangles? The answer is yes, using the law of sines and law of cosines. So an oblique triangle is a triangle that does not contain a right angle. An oblique triangle either has 3 acute angles, all less than 90 degrees, or it has 2 acute and 1 obtuse angle. A triangle cannot have more than 1 obtuse angle, or else it would have a total of more than 180 degrees. The relationship among the sides and the angles of right triangles defined by the Pythagorean theorem and the trig functions don't apply to oblique triangles. You can't use a squared plus b squared equals c squared on something that's not a right triangle. However, we can still use trigonometry to solve for the missing parts of oblique triangles using either the law of sines or the law of cosines. And by the time we finish the law of cosines, you'll be able to tell which law you need to solve based on the information that you're given. So the law of sines says if capital A, B, and C are the measures of the angles of a triangle, and little a, b, and c are the lengths opposite each of those, little a is opposite capital A, little b is opposite capital B, and so on, then the law of sines says this: the ratio of A to sine of big A equals the ratio of B to the sine of angle B equals C to the sine of angle C. And it doesn't matter whether you put the sides in the numerator and the sine of the angles in the denominator, or the sine of the angles in the numerator and the sides in the denominator. But all that's saying is for any triangle, one ratio of the length of a side of the angle to the sine of the opposite angle is the same no matter which side and which angle you're talking about. So you give me 3 bits of information, actually 3 particular bits of information, and I can find all the missing parts. So objective 1, use the law of sines to solve oblique triangles given the length of one side and 2 of its angles. Actually, I said after we finish law of cosines, you'll be able to distinguish when you can use law of sines and when you can't, but I can go ahead and tell you that now. If you have one complete ratio of a side and an angle opposite it, then you can use the law of sines. So in checkpoint 1, we have 2 of the angles and a side, but that side doesn't happen to be opposite either one of the 2 angles that were given.
Can we add the angle?
Yeah, it's really easy. If you're given 2 of the angles, then it's easy to find the 3rd one. So we can find angle B and then use law of sines because we have side B. All right, so I'm not even going to try to draw that triangle. I'm just going to say angle B is 180 degrees minus 40 degrees minus 22.5 degrees. And I've got my answers here just so we can move through this quickly. That's 117.5 degrees. Now that we have side little b and angle big B, we can use the law of sines. And it doesn't matter if we find side A or side C first. Any, meeny, miny, mo, if you want to find side A first, then you would have A over what? sine 40 degrees, because each ratio is a side and the sine of the angle opposite it. So A over sine 40 degrees equals what? Well, over sine of 117.5 degrees. And the only thing you have to do to have the A by itself is what? Multiply by sine of 40 degrees. So A is 12 times the sine of 40 degrees over the sine of 117.5 degrees. You'd need your calculator in degree mode because that's what we're given. And I got it to be 8.7. We're not given the units on those sides, so I don't know if that's 8.7 inches, 8.7 kilometers. I don't know.
So far, everything else we've done is gonna be in radians, right?
No, this is the length of a side.
I mean, before this. Like, everything that was before this unit, or not unit, it's sorry.
We've dealt with angles given in degrees and given in radians. We've dealt with both of them, but a side is neither degrees nor radians. A side is inches or feet or
We're talking about degree mode on the calculator. Most
Oh.
of the test is gonna be in radian mode, correct? Except for this part.
I think we've dealt with both. We probably dealt with radian more than degrees, but we've used degree mode before, so I don't want to say all except for this is radian mode. All right, so what are we missing? Triangle has 6 parts and we have 5 of them. We need to find what now? C. So C over sine what? 22.5 is angle C, so sine of 22.5 degrees. And we can use the same 12 over sine of 117.5 degrees for our other ratio. Actually, if we were working for NASA, we would want to use what we were given, not what we rounded. So I would use the side B rather than the side A. A would be 12 sine of 22.5 degrees over sine of 117.5 degrees. And you can double check it, but I got that. I'm sorry, what? Oh, that is a C. Yep. I copied down what was directly above it. C would be about the nearest 10th. I got 5.2. All right, pretty easy. So far, so good. Objective 2 is use the law of sines to solve oblique triangles, if possible, given 2 sides and an angle opposite one of them. In objective 1, we had 2 angles and one of the sides. If we had 2 angles, it's easy to find the third angle. But this, we're given different information. We're given 2 sides and an angle opposite one of them. That's called the ambiguous case of the law of sines. I don't like ambiguity, but it happens sometimes. Actually, let me show you a website. Let me show you this website I have pulled up. I think it'll make it more clear than my pictures here. You have my pictures for reference later. But let me show you why this is called the ambiguous case. All right, we're going to be given an angle. Here we're given angle 40 degrees. And we're going to be given one of the sides. Here we're given B equals 9. You can tell that for a side of length 4.7 for A, that's just too short to make an angle. if you're given a 40-degree angle and a 9-degree side there, then the side opposite it would have to be just the perfect length in order, see if I can catch it. In order to, sometimes I can hit the exact length, sometimes I can't. To just make one triangle, there's only one specific, come on, one specific length that A could be that would form a right triangle. Well, I can't nail it right now. But if A was exactly this length, then there would be one triangle and the one triangle would be a right triangle. No, that's not true. It wouldn't have to be a right triangle, but you'd only get one triangle. If that side A was too short, then you just have no solution. You can't build a triangle with the information you gave me. And then the third scenario is what's on the screen right now. If A was 5.9, it would actually intersect that horizontal line twice, and there would be two triangles. It'd be two solutions. So when you have the ambiguous case of the law of sines, the three things that can happen depending on this side A are no solution, exactly one solution, or possibly two solutions. And we'll have to figure out in each problem which one of those three scenarios we're facing. So, through with that. My illustrations are showing the same thing, just side A is not swinging in the air. If side A is too short, you get no triangle. If side B is just side A is just the perfect length, then you get one right triangle or one obtuse triangle. And then really both of those I said were one case. You get one triangle, no triangle, or two triangles.
In this case, if you only are given.
When you're given an angle opposite one of the two sides. Yeah, you'll know when you see it. All right. So at point 2, solve the triangle with A is 50 degrees. Side A is 10 and side B is 20. And I'm going to go ahead and say, how do you, other than the fact that we haven't covered law of cosines yet, how do you know you can use law of sines on this? You have both of the A's, that works. You have one side and the angle opposite it. You have one complete ratio for the law of sines. So if we're given side B, what do you think we should find first?
C. No, the B.
Let me ask you this, Rachel, how would we find C?
Is it
Right. We can't use the Pythagorean theorem to find C because this is not a right triangle. So all I can find with the information that I'm given is B, angle B. And I like to set up the thing that I'm looking for in the numerator like I did here when I was looking for A. I put A in the numerator so that all I had to do is clear out fractions. In this one, since I'm looking for angle B, I'm going to put sine B in the numerator. And that ratio would be sine B over 20 equals sine of 50 degrees over 10. And all I have to do to solve for sine B is multiply both sides by 20.
No, never mind. I wrote it.
Okay. She could reduce that to sine B equals 2 times the sine of 50 degrees. But I don't want to know what sine of B is. I want to know what B is. So how do I find that? Inverse sine, B would be inverse sine of 2 times the sine of 50 degrees. And what do you get when you punch that on the calculator?
So we put this in degree mode because we're using degrees.
Correct. Using degrees, and so you want your answer in degrees, and so you use degree mode. Domain error? Does that mean you left your calculator in the car on a freezing night, or your batteries are dead, or something else? It means what?
The side's
Why?
not long.
Because the side's not long enough? Why is your calculator telling you domain error though? I think you're right. It's no triangle because one side's not long enough, but why is it that your calculator is saying domain error, Ms. Madison? 2 times the sine of 50 degrees is more than 1. And so if I had gotten a decimal approximation of that, let's say it turns out to be 1.7, I don't know what it turns out to be, but whatever it is, it's a number that's greater than 1, so I can't take inverse sine of that number. So this triangle or this solution, there just isn't one, no triangle, because 2 sine 50 degrees is greater than 1. Which is exactly what domain error means. When you're using inverse sine, any number greater than 1 is not in the domain of inverse sine. All right. So when you're evaluating inverse sine to solve an oblique triangle, how can you tell that there's not going to be a solution?
It's not.
Your x is either greater than 1 or less than -1. The short way to write that is the absolute value of x is greater than 1. X were -1.7, you take the absolute value, that's greater than 1. So there would be no triangle that exists with the information you're given. How could you tell solving or using inverse sine of x? How could you tell when you're going to get just one right triangle?
Could you like the sides, like could they be a squared plus b squared is c squared because right triangles?
Well, that's after you found everything. You can prove it's a right triangle,
Yeah.
but we haven't found everything yet. Austin, did you have an idea?
Sine angle A, not sine angle, but angle A and angle B. If angle C is 90, then
But I don't know all the angles yet, or I don't know, I'm trying to use inverse sines, and I'm trying to figure out what would cause inverse sine to just give me one right triangle. Madison, what are you thinking? Equal 1. 90-degree angle. So how can you tell when there will be one right triangle when x equals 90 degrees or pi over 2
What about
radians? Then when you take sine of that, you're just going to get 1. And your solution is going to be one right triangle. Tell me what you're thinking.
what about 3 pi? It's -1, but like what if it was like no?
You, in the Cartesian coordinate system, you would have, it doesn't even really make sense to say upside down triangle. you would still have, it would still be one right angle. You can't take the inverse sine of 3/2 pi because it's not a number between -1 and 1.
Okay, so you're talking about taking the radians, not the. Like 0 to 1. Okay,
Yeah, I didn't get that. But you're good?
yeah,
Okay, okay.
yeah.
How can you tell when there are two possible solutions?
When it's not 1 and then it's in between -1 and 1.
Right, when X is between -1 and 1, not including -1 and 1. I don't have, and this may have been what was bugging you. I didn't mean when X is 90 degrees or when X is pi/2. I meant when X is 1. The number that we're taking the inverse sine of is 1, then we're going to get one right triangle. So no solution when X is greater than 1 or less than -1, one right triangle when X equals exactly 1, and then two possible triangles when X is between -1 and 1, not including -1 and 1. Let's save this fourth question for a minute, do a checkpoint 3, and then see if we can answer. Could there be, looks like if there are going to be two triangles, but for some reason, one of them has to be rejected. That's going to be the real nuisance. All right. Checkpoint 3. Solve a triangle with angle A equals 40 degrees, side A is 54, side B is 62. Other than the fact that we haven't covered law of cosines yet, how do you know we can use law of sines? We have both angle A and side A. And we have side B, so what should we find first? Angle B. All right, we need angle B. So sine of angle B over B, which is 62, equals sine of 40 degrees over 54. And so sine of B equals 62 times the sine of 40 degrees over 54. And we can get a decimal approximation of that right-hand side and tell whether there's going to be no solution, one solution, or possibly two solutions. I want to get a decimal approximation of that, but I don't want to round it. I want to keep all the numbers on my calculator screen. Tell me, without writing it down in rounded form, approximately what is that right-hand side? Is it equal to 1, less than 1, or greater than 1? It's the right-hand side's greater than 1? I don't think so. I think it's less than 1. Punch it again and make sure your calculator's in degree mode. I'm not talking about inverse sine yet. I'm just talking about punching that right-hand side. It's less than 1. So that tells me there are two possible solutions. I'm going to make myself a little note right here. That is less than 1. And that's how I know there are two possible solutions. We're going to have at least one, but maybe two. So how am I going to find beta? Inverse sine of that right-hand side. And if you still have all those digits on your screen, all you have to do is enter the inverse sign. And the directions say round measures to the nearest whole number. So how many degrees is B to the nearest whole number? 48 degrees. Now, how can there be any other solution? This is a positive number in parentheses, right? Positive number less than 1. In what other quadrant am I gonna have an angle whose sine is the same thing? The other angle where sine is, or the other quadrant where sine is positive is angle 2. So I have this first quadrant angle. You good? That's okay. In quadrant 1, how do I find the quadrant 2 possibility? Yep. The first quadrant angle is 40 degrees from the positive x-axis. I also want the angle that's 48 degrees from the negative x-axis. So I'm going to call that my possible angle B1. And then my possible angle B2 would be 180 degrees minus 48 degrees, which would be 132. So 132 degrees. This is a positive number. This right-hand side is a positive number less than 1. So where is sine positive? And the calculator gives me the first quadrant, but then I have to use that to find the second quadrant. So here are 2 possible angle betas. Now, I need to start writing carefully here. I'm just going to draw myself a line and finish solving triangle 1 in the left column. And if there is a second triangle, I'll find all of its parts in the right column. What I know now about triangle 1, and I'm just trying to keep all my stuff organized here. Triangle 1 has A is 40 degrees. Side A is 54. Side B is 62. And angle B is 132 degrees. That's the 4 things I know. I don't know. But it doesn't matter which one you find first. I could have found the 132, but I don't know why I did that. I just looked up and saw it. B1 is 48 degrees. So what would be the easiest thing to find next?
Angle B.
Yeah. And how would I find the angle C? Subtract the 2 angles I know. And you have 180 degrees. That is the distributive property of real numbers. You're just, yeah, you're just subtracting both. The reason I'm saying that's the distributive property, you're saying 40 plus 48 subtracted from 180. And what everybody else said was 180 minus 40 minus 48. So just distribute that negative like that. All right, so 180 minus 40 is 140 minus 48 is what? 92 degrees. How many parts of triangle one do we have now? We have 5 parts. What's the only part we're missing?
Side C.
Side C, how can we find it?
So, big A and little a, side A and 40 degrees. Ratio is 2 to 6.
Tell me this, could I use, since I know A and B, could I use the Pythagorean theorem to find C? No, this is not a right triangle. I know all 3 angles and none of them are 90 degrees. So I have to use the law of sines. I'm looking for side C, so I'm gonna put side C in the numerator over sine of angle C. And by the way, this angle that I just found, that 92 degrees, I'm gonna call it C1 because it's the angle in the first triangle. I may end up with a side or a C2 in the right-hand column. All right, side C over sine of 92 degrees equals sine. I'm going to use what I found rather than what I was given rather than what I rounded. So A is 54 over sine 40 degrees. And I'm going to call this side little c1, again, because it's part of triangle 1. C1 would be 54 times sine of 92 degrees divided by sine of 40 degrees. And I got that to be to the nearest integer. To see 84.
Yes.
And I don't know the units on that side. All right, so I definitely have one triangle solution based on the information I was given. Now I know there's a possibility that I have a second triangle for which angle B is 132 degrees. So what would be easiest to find?
Angle C.
Okay, I'm going to write down like I did for triangle 1. I'm going to write down everything I know about triangle 2. I know A is 40 degrees. Side A is 54. Side B is 62. Angle B2 is 132 degrees. So now I have 2 angles. I can find the third angle and I'll call it C2, the missing angle from triangle 2. C2 would be 180 minus 40 minus 132. That's just 8 degrees. Yeah, just 8 degrees. Now think back to the question we skipped here. In checkpoint 3, we had 2 possible triangles. One of them definitely worked out. We found all the missing parts. The other one, can you think of anything that could have happened with C2, that's angle C for the second triangle, that would have caused this triangle 2 to not be real? And by answer, you mean answer for what? Angle C. Angle C. If angle C turned out to be negative, well, I can't have a triangle with a negative side. So I could say, I could answer this question when the sum of the other 2 angles is greater than 180 degrees. If the two angles you know already add up to 180 or more, I guess I could put a greater than or equal to there, then there's no room for a third angle. And I don't think we'll do one of those as an example. We may. Or may not. I may skip checkpoint 4 because we still have so much left. If we don't do one where we reject the second triangle, it'll be because the sum of the two other angles is greater than or equal to 180. So let's finish this one. We have our three angles. We need our side C, side little c 2. So side C2 is the sine of 8 degrees equals 54 over sine of 40 degrees. So C2 is 54 sine 8 degrees over sine 40 degrees. And I got that to be approximately 12. Okay. At the bottom of the notes, I have, or bottom of this page, I have an illustration of the two possible triangles that have the information that we were given in checkpoint 3. We were given that angle A was 40 degrees, side A was 54, and side B was 62. That side A was long enough to cause there to be two triangles. In part B and part C here, I have the two triangles split out. So you can see that one of them is a triangle with 3 acute angles, and then one of them is a triangle with 2 acute angles and one obtuse triangle, or one obtuse angle. All right, how we doing? Let me just say, because I really want, I really want to get to objective 3 and 4. Let me just tell you on checkpoint 4 what happened. And don't try to write this down or anything, but I was fooling along just like I had been on checkpoint 3. I got sine of a number between -1 and 1, which told me there were 2 possible triangles, and I found all the missing parts of the first triangle. But when I went to find the parts of the second triangle, I already had A is 57 and B is 138. That leaves no room for an angle C. So you can just quit right there and say there's only one solution, and it's the first triangle. All right, let's skip that one. I think y'all will be able to handle it if you saw it in the homework. You might not anticipate it's coming, but as soon as you subtracted the other 2 angles from 180 and got a negative, you would know. All right, so objective 3. Find the area of an oblique triangle using the sine function. We know how to find the area of a triangle. Tell me in words how you would find the area of that triangle.
Space.
1/2 base times height. No, you're just multiplying 2 numbers, whatever the base is. Oh, where is my half? No, you don't have to have them in parentheses. It wouldn't be wrong if you did. The reason you wouldn't have to have that in parentheses Haley, is because, that's a product, not a sum, so you wouldn't distribute the 1/2. That's just. These mean, I wrote that so poorly. Area equals 1/2 base times height. And you don't have to have base and height in parentheses because they're multiplied, not added. If I had a triangle that had base 4 and height 7. Just do a 1/2 times 4 times 7.
Okay, that's fine.
Yeah, you don't have to have the 4 times 7 in parentheses. You could take 1/2 of 4 is 2, and then 2 times 7 is 14. All right, so that's the base times height. Using the labels that I have used for this triangle in the illustration, which variable is the base?
C.
That's C, and the height is H. So using the triangle shown, I would say area equals 1/2 CH. Only because I labeled the base C instead of B, no big deal. All right, in terms of the triangle shown, what is sine A? Look at this angle A and tell me what sine A would be.
Or A over C.
Well, sine only applies to right triangles, and my right triangle is right here. H over B. Sine A is H over B. Express H in terms of angle A and side B. If you solve the previous line for H, what would you have?
Oh, B sine A.
B sine A. And so can we turn this formula that we had on our second line here, A equals 1/2 CH? Can we turn that into a formula that has angle A, side B, and side C instead of having an H in it? What could I put in place of that H? Yeah. Area would be 1/2 times C, and then in place of H, I could put B sine A. Don't have to have the dot, but it's helping my eyeballs. It's helping me see that B sine A is just in the place of H. So we just found a formula for finding the area of a triangle when we know one angle and the two sides opposite it. The area of a triangle is half the product of the lengths of the two sides times the sine of the angle between them. So if you give me A and C, then you have to give me angle B. Or if you give me A and B, then you have to give me angle C. But if I have that, I can find the area of the triangle. So at point 5, find the area of the triangle having two sides of length 8 and 12. And it doesn't matter which side you call 8, which side you call 12. But if you want to stick with the formula we have above, then one of those sides is C and one of those sides is B. And the 135 is the angle between them. That's angle A. So the area Ooh. I don't like using A for area and A for an angle. What can I do about that? That would work. Or sometimes we use a shape as a subscript. That means the area of the triangle is B times C times sine of the angle between them, and all of that times a half. B times C sine of A. And you can just do that left to right. Half times 8 is 4, 4 times 12 is 48. So it's 48 sine of 135 degrees. If I ask you for an exact answer, or if I ask you to round it to the nearest tenth, then that would be 30. I didn't round to the nearest tenth. What would it be? I got 34. 33.9. I'll that on review day because I don't remember. 33.9 and meters.
Meters.
Yes, meters squared, because we're talking about area, not one-dimensional length. All right, I at least want to get the two equations set up for these two word problems. I'm going to get my picture drawn right. Then if we have that, I bet you wouldn't have a problem solving the equation after you set it up. Problem 1 says a pine tree growing on a hillside makes a 75-degree angle with the hill. All right, here's the hillside. And here's my angle that the tree makes with the hill is 75 degrees. From a point 80 feet up the hill, that's 80 feet up from the pine tree, right? So here's the pine tree, and then up here somewhere, there's a person, and from the pine tree to the person is 80 feet. The angle of elevation to the top of the tree is 62 degrees. Well, here's the top of the tree. Here is an angle. Is it saying that this whole angle right here is 62 degrees? What does angle of elevation mean?
In respect from,
Always with respect to the horizontal. Is this hill horizontal? No. I've got to draw me a little horizontal in there. Angle of elevation and angle of depression are always, always, always with respect to the horizontal. So this is 62 degrees right there. I'm going to make you a note right here with respect to the horizontal. And the angle of depression to the bottom of the tree is 23 degrees. That's also with respect to the horizontal. You can use the same horizontal. See, I like that this book uses line of sight. This is a person's standing right there. And that dashed line is them looking straight. They have to look up 62 degrees to see the top of the tree. They have to look down 23 degrees to see the bottom of the tree. Miss Ellie, is that okay? Can you ask me something? Right there. Okay. What am I looking for? The height of the trees? So let's let that be X. Just a center line straight down through the tree. Do I have what I need to use the law of sines right now?
No.
I don't have, if I was looking for X, I'd have to know the angle opposite it, and I do, but to use the sine of 75 degrees, I'd have to know the side opposite that. So what can I find? You're calling this missing angle of the triangle up here C? Okay.
See?
So C would be 180 degrees minus 75 degrees minus what?
62.
Or add them and you get 85 degrees. And so C was what? I didn't hear you. 20 degrees. And now what equation can we set up? Not
20 over 80.
equals,
Some 85. Need to flip it.
oh, okay, okay, gotcha. X over sine of 85 degrees, that is one side and the angle opposite it, equals 80 feet over sine of 20 degrees. And I'm just gonna let you finish that one. So we can set this other one up really quickly. Is that okay? All right. Last one, just set up. Number 2, after a windstorm, you notice that your 16-foot flagpole may be leaning, but you're not sure. Here's the hard way to find out if your flagpole is leaning. From a point on the ground, well, let's draw the flagpole first. It's a flagpole, it's 16 feet, and it may or may not be exactly perpendicular to the ground. I meant to make it look like it's not. I better do that or else you'll think it's a right triangle. Let's say it's just a little bit off. I know. Okay, that is obviously leaning. And the ground's not even level, we'll play like it was. All right, 16-foot flagpole may be leaning, but you're not sure. From a point on the ground, 15 feet from the base of the flagpole. Here's the base of the flagpole and 15 feet between those 2 points. You find that the angle of elevation to the top is 48 degrees. That means you're standing right here. Well, you're probably standing above the ground rather than below it, or your eyeballs are on your toes or something. With respect to the horizontal, that angle is 48 degrees. Is the flagpole leaning? What is that even asking me to find?
We don't know if it's.
We don't know if that, I'm labeling it angle B, is 90 degrees. So what would be my equation? I have one complete ratio. Wait, I have my one complete ratio. Look at me. My one complete ratio is 16 to sine of 48 degrees. And I don't know that side or that angle. How do I find the top angle, oh, because I know this, because I know the side opposite it. So let's call this C. And we can say sine of C over 15 equals sine of 48 over 16. I'm gonna let you finish it.
Yeah.
Once you know C, if C and 48 add up to be 90 degrees, then B is 90 degrees. But if C is not 42 degrees, then B is not 90 degrees. Alrighty, next to last homework. Yeah, the what? You all understand.
No. We have to take it up.
Oh, no, because there's not gonna be,
After goal.
all you want to know is if this is 90 degrees or the second. If you call this a first quadrant triangle, there would be a second quadrant triangle, but if this is 90, that would be 90 also. And if that's not 90, then you've answered the question, it's not, everything like always leading.
And what? That I see.
You will find out if you try to find C while you have to reject the second. It'll end up that this one plus that one's already more than 180, so you're not gonna get that other one. Okie dokie. Oh, I gotta stop recording.